All right, welcome to this explainer. Today we're diving straight into the real engineering math behind picking the right battery voltage for your off-grid system. We're going to prove mathematically why a 48-volt battery bank isn't just a friendly suggestion for a 6 kilowatt setup, it is absolutely mandatory. If you've ever wondered how the pros design systems that, actually work without overheating, failing, or just wasting energy, you are in the exact right place. So, is battery voltage just a matter of personal preference? A lot of beginners make this super dangerous assumption that picking a voltage is just, well, a personal choice. Kind of like picking the color of your inverter. They think, hey, I've already got a bunch of 12-volt batteries lying around, I'll just string them together for my massive off-grid cabin. But today, we're going to completely bust that myth. We've generated a detailed visual breakdown based on these slides to look at the hard numbers and show you exactly how battery voltage literally dictates the entire safety and efficiency of your whole setup. Here is our roadmap for this explainer. We'll start with the battery voltage myth, look at the inverter bottleneck, do a quick 12V reality check, uncover exponential power loss, and finally look at exactly why 48 volts wins. All right, Section 1, the battery voltage myth, the knowns and unknowns. Let's take a look at the actual problem we're trying to solve here. On the known side to the left, our load requirement is about 4.7 kilowatts, so we've wisely picked a 6 kilowatt inverter to give ourselves a nice safe buffer. But look over at the unknowns on the right. Choosing between 12V, 24V, and 48V, that is not a stylistic choice, folks. That decision directly dictates your system's current, the physical size of the cables you have to buy, your heat loss, and the overall reliability. The question mark isn't about what we prefer, it's about what the physics of a 6 kilowatt load will physically demand from your battery bank. Moving on to Section 2, the inverter bottleneck, power conversion. Now, to output 6 kilowatts of AC power to your house, that's on the right side there, the inverter has to draw that entire 6 kilowatts of DC power from the battery block on the left. Think of the inverter like a toll booth. It doesn't magically create power, it just transforms it. So if your house is demanding 6,000 watts to run, say the well pump, the fridge, and the lights, the inverter turns right around and pulls 6,000 watts directly from your batteries. That is exactly where the bottleneck happens. And depending on your voltage, the current loads right here can get absolutely enormous. Which brings us to Section 3, the 12V reality check. Math meets reality. Okay, we are now looking at the literal fundamental equation of electrical engineering. Current equals power divided by voltage. Look at this seesaw scale. The power in the center triangle is locked in at 6,000 watts. Because that power number is a fixed requirement, the voltage and the current are trapped in an inverse relationship. As the seesaw visually proves, for that exact same 6,000 watt output, pushing the voltage up automatically forces the current to come down. They balance each other out perfectly. Let's actually run those numbers for our 6,000 watt inverter. If we divide 6,000 by a 12-volt battery system, we get a highly dangerous 500 amps. If we step that up to 24 volts, we cut the current in half to 250 amps. Better, for sure, but still really high. But look at the green box. At 48 volts, the current drops to a completely manageable 125 amps. It's the exact same amount of total power being delivered to your house, but the physical stress on your system, radically different depending on which voltage you choose. To see what 500 amps actually looks like in the real world, check out this terrifying visual contrast. Up top, you've got the massive cable required just to survive a 12-volt system running 500 amps. Guys, we are talking about welding-level currents here. That cable is thick, it's incredibly expensive, it's a total nightmare to bend during installation, and honestly, if you have even a slightly loose connection, it is a severe fire risk because of the sheer volume of electrons trying to squeeze through. Right beneath it, that's the safely scaled 48-volt wire handling 125 amps. It's normal, it's workable, it's safe. Running a 6 kilowatt inverter on 12 volts virtually guarantees thermal problems down the line. Next up, Section 4, exponential power loss, the hidden killer. Here's the thing. Power losses in cables don't scale normally. The formula for power loss is current squared times resistance. Now, I really want you to focus on the word squared in step 1. Because the current is squared in the math, the heat generated grows exponentially. As you can see in steps 2 and 3, if your current becomes 2 times larger, your power losses don't just double. They become 4 times larger. You literally quadruple your heat and wasted energy just by doubling the current. Crazy, right? Let's apply that exponential math to our real-world setup. Let's compare the 12-volt system to the 48-volt system. Our 12-volt system draws 500 amps.
That is exactly 4 times larger than the 125 amps drawn by the 48-volt system. But remember the formula. We have to square that difference. 4 squared is 16, meaning by choosing 12 volts over 48 volts, you suffer a shocking 16 times more energy loss and heat generation in your wiring. This massive 16-fold jump in wasted energy is the #1 reason engineers simply bump up the voltage rather than wrestling with these huge, dangerous currents.
Finally, Section 5, why 48 volts wins the industry standard. Look, there is a right tool for every job. 12-volt systems absolutely have their place. They're great for camper vans and small portable lighting setups. 24-volt systems, perfect for moderate loads, like a small weekend cabin. But look at the bottom row. For 5 to 10 kilowatt inverters handling heavy daily residential loads, 48 volts is the undisputed standard. You wouldn't use a bicycle to tow a freight train, right? And you definitely shouldn't use a 12-volt battery bank to run an entire house. And this is precisely why top-tier professional inverter manufacturers operate the way they do. Look at these brands on the right: Victron, Day, Groat, Voltronic. Almost all serious 5 to 6 kilowatt inverters from these companies are built exclusively for 48 volts. Honestly, they don't even give you the option to run them at 12 volts because they know the math we just went through. By designing for 48 volts, they guarantee you can use standard, affordable fuses, workable currents at 125 amps, normal-sized terminals, and cable runs that won't literally melt inside your walls. Let's quickly review the final engineering cascade we've mapped out in this explainer. It's essentially a domino effect of good design. Step 1, you choose a higher battery voltage, specifically 48 volts. Step 2, this guarantees a dramatically lower current of 125 amps. Step 3, because of that low current, you get minimal heat and cable losses. Step 4, this naturally leads to much higher overall system efficiency because you aren't wasting your precious solar power just heating up thick copper wires. And finally, Step 5, the ultimate goal: a safe, reliable, off-grid system that you can actually trust day in and day out. So, we've officially busted that beginner myth we started with. As this quote perfectly summarizes, choosing the battery voltage is not simply a matter of preference. It is an engineering decision based on current. It's not a personality choice, guys. It's an unavoidable mathematical reality. When you're designing a system, your power requirements dictate your current, and you simply must choose the voltage that keeps that current in a safe, manageable range. So I'll leave you with this final thought. Knowing that a 12-volt setup creates a staggering 16 times the heat and energy loss of a 48-volt system for the exact same power output, are you really still willing to base your off-grid system on a simple preference? Take the engineering logic we've detailed in these slides with you as you design your own setup. Let the math do the heavy lifting. Keep your current low, and let the engineering keep your home safe and highly efficient. Thanks so much for joining me on this explainer, and I'll catch you next time.